Hey, Ji, welcome to the lecture. Today we'll be discussing Unit 21 from your book. And the topic's name is Secured, in which we will be looking at basically different methods of encryption. We will also be understanding the difference between asymmetric and symmetric encryption. What is the use for hashing? What are, uh, digital certificates? What's the difference between a digital certificate versus a digital signature? We will also be looking into detail with regards to what quantum cryptography is, what different techniques regarding symmetric and asymmetric encryption is used, and also the underlying working of your secure socket layer as well as the TLS protocol. Okay, so first of all, we need to understand the fundamentals of encryption. The process of encryption involves converting plain text, that's the data that is before it's being hidden, and that's converted into a basically unrecognizable format, which is known as ciphertext. Ciphertext is the result after applying encryption algorithm to data for safely storing and transmitting data using computer technology. Now, obviously, encryption, whenever we're talking about internet data transmission, we are relying on wireless data transfer. And what you understand about wireless data transfer is that it's being broadcasted over your transmission channels. Now, what that could possibly result is that data being falling in the hands of people who are unauthorized to view the data. So to help protect with that, we have certain techniques, which such as encryption, which allows that even if it does fall in the wrong hands, it's never really understood. So basically, people who are not authorized to access the data are receiving only encrypted text, because of which, even if they do receive the message, they will not understand what's going on because it's all in encrypted format. Now, obviously, encryption should be a reverse procedure, because if it would be no good if I can encrypt it but never decrypt it. So obviously, when I'm sending data, I should to my intended recipient. My intended recipient should at one point be able to convert it back into its original format. Okay, encryption becomes essential when data needs to be sent while maintaining confidentiality. Only intended recipient should decrypt data. So that means, so you are maintaining secrecy of what message is being sent, and any unauthorized access will not result in any information or loss or information revealing to unauthorized users. Authenticity, the receiver must be sure of who sent the data text. So you will be, there are techniques that ensure that you are confident that message is coming from the person who really they claim that who they are actually who they claim to be. And most importantly, integrity, data must not have been changed during transmission. So if there is some unauthorized user, or maybe it's because of some sort of data corruption, if the message has been changed during data transmission, you should not be you should be able to highlight that on your end. And if there is some change, you should be able to block the use of the data, so preventing any further damage. And non-repudiation, that means neither the sender nor the receiver should be able to deny that they were part in the data transmission. So if someone sent a message, they will have a stamp, they will have information that proves that they are really, in fact, they were part of the message. And if you are intended recipient, you will also be held accountable for receiving the data. Finally, availability, the receiver should not be prevented from receiving the data transmission. So the intended recipient, upon being sent the data, should be able to receive the data at all times. Now, there are basically two things that we need to be clear. First of all, encryption algorithm. It is usually public, whereas the encryption key, the key that was used to convert your plain text into ciphertext, that is kept secret. Encryption techniques are usually falling in two categories. There is symmetric encryption, whereas asymmetric encryption. Symmetric encryption means that I'm basically using the same key. There's one key for encrypting data as well as decrypting data. So if when I'm sending data, I will encrypt it using symmetric encryption, and using the same key, the intended recipient should be able to decrypt the data. Now, the problem obviously is with symmetric encryption is that that key has to be, the same key has to be both with me and the sender and with the receiver. Now, if, for example, the sender and receiver are far apart, that would mean that I have no means of sending that key to my intended recipient. And if I use the channels to send the key, the same channels that I'm using to send data with, there's a great chance that the an unauthorized user who is listening into our transmission will receive the encrypted data as well as the key that is used to decrypt it. So basically that defies the purpose of encryption altogether. So in which case, this is a problem. Symmetric encryption has this problem, and this is known as the key distribution. How will I be able to transfer? How will the sender and receiver be able to share keys? Now, this key distribution problem has been addressed with a couple of methods. We'll be looking into this later. Now, but this is basically what symmetric encryption is. Both sender and receiver using the same key for, and in short, it's the same key is used for encrypting data as well as decrypting data. Now, the second method is a more secure method, and this is known as asymmetric encryption. Now, asymmetric encryption means that there is a key pair. There's a public and private key pair, and by pair, it means that there are matching keys. So if I'm using a public key, it has to be matched with the same private key. And those private key A with public key B will not match. So it has to be public key A and private key A to be used together. Now, obviously, as the name suggests, public key is publicly available. It's known to everyone. And in this particular in this particular scenario, public keys are only used for encrypting the data. So when the intended senders encrypts the data for the intended recipient, the data is sent using the intended recipient's public key. When the data is sent over your internet or broadcast over the internet, the intended recipient, upon receiving the data, will apply his or her private key, because of which only then data will be revealed. Anyone else receiving the data may apply their private key, but since the key pairs exist and I used user A's public key, the only user A's private key will be applicable on the data. User C and D will not be able to decrypt the data using their own private keys. So this is only a matching key pair. So this is a very secure method. I mean, and this basically solves the problem of key distribution. And we can also carry out symmetric encryption using asymmetric encryption. Now, one of the methods of solving the key distribution problem in symmetric encryption is that instead of sending the message collectively, I simply send the key, only the key. I encrypt the key, just the key, using asymmetric encryption and transfer it to my intended recipient. Now, since we know that asymmetric encryption is very secure, using that secure method, my intended recipient will eventually have the same key that I have because I have used asymmetric encryption. Now, and there is confirmation, there is guarantee that no third party or non-authorized user will have listened to that transmission. And even if they did listen to transmission, they will have encrypted that and they will not be able to decrypt it because I used public private key encryption. And the only way that anyone can decrypt data is by using their private key, the matching pair private key, which the unauthorized user will not have. So in case this asymmetric encryption is secure, then I can even use this method to transfer the symmetric key that is to be used for both sender and receivers. Now, this is one diagram which sort of explains what's happening with your encryption procedure. So basically, I have my, as we have studied flowcharts, and if you remember a flowchart, this symbol represents input and output. So basically, plain text is given as an input to this process. Now, this is a process block, so the encryption is a process. Now, plain text and the key are given as inputs to the process of encryption, which results as an output of ciphertext. On the receiving end, my receiving computer takes the ciphertext as an input, and the key is applied to the process of decryption, coupled with the ciphertext, and the resulting output of this procedure is known as the plain text. Now, this is a very simple representation of what basically the process of encryption is. For the key to be effective, the encryption algorithm must be complex, and the number of bits used to define the key must be large. For example, 128-bit key. The larger it is, the more difficult it is to crack, or more difficult it is to determine. So these are the methods that we are using for the hiding data. Now, in the second part, now we'll be discussing what a digital signature is. Basically, digital signature means that I have created a method in which I can basically authenticate a particular user on the internet. So basically, if someone is sending the data to me, if sender A is sending some information to me, I should be able to be, sure that it really is sender. So there are some methods, certain methods that can be used sort of to, create a signature online to prove that you are who you claim to be. So basically, this involves another technique which is known as hashing. Now, hashing, as opposed to encryption, is a different method. Now, the biggest difference between hashing and encryption is that hashing is a non-reversible process. So basically, that means is that encryption you can get from plain text to ciphertext and ciphertext back to plain text. But hashing means that you go from plain text to a hash value, and there is no way that you can recreate the plain text from a hash value. So it's basically an irreversible process. And you might be wondering, why is that necessary? Because we were considering that it should be reversible because the intended recipient should be able to understand what data is being sent. That's very actually important here, because hashing really is not meant for hiding data. Encryption was meant for hiding data and unhiding data eventually, but hashing, the purpose of hashing is different. Hashing is used for basically making sure that the data is basically not altered in any way. So basically what happens is that I, using a hashing algorithm, and apply the hashing algorithm to my plain text, and this will generate a hash value, which is, this hash value is also known as a digest. Now I will send this hash value to my intended recipient. My recipient will use the same algorithm to recreate another hash value on its own side. So the hash value that it's received, the sender, the sender will take the hash value that it has received and compare it with the hash value that it has calculated. If both hash values are same, it means that message has not been changed. So basically, hashing not only helps in authentication, it also helps in integrity. So if the message has been changed in any way, the resulting hash value that I calculated in my receiving end will be different, because of which I should not be trusting that message. So this is another way that I can improve the integrity of my internet communication. So a mathematical technique to authenticate and validate the integrity of a message. Using digital signatures, we can assure that a message was sent by a particular sender only. If digital signatures are not used, data can be altered, and also the sender can also be manipulated. So what happens in this digital signature creation method is, now these steps are actually pretty simple. Programs like emails create a one-way hash value. So again, it's one way because it's not a reversible process of data that is to be signed. This is known as digest. So basically, I apply a hashing algorithm on the entire data, and a hash value is generated. This hash value is encrypted using a private key. Now, this is interesting. Asymmetric encryption, we just studied asymmetric encryption just a while ago, and we saw that encryption in asymmetric encryption, the encryption process is done using the public key. Now here we can see that when creating a digital signature, we're using a private key. It's the opposite technique. So instead of using public key to encrypt, we're using a private key to encrypt. Now this is interesting why this is necessary here. But anyway, let's focus on what's happening here. Anyway, so the digital signature, which is the encrypted hash value, which we just used using my, for example, if I'm the sender, we're using my private key, combined with the hashing algorithm, is appended to the actual data which is to be sent, right? The receiver, upon receiving the hash value and the digest, will recreate the hash value again on the data received. Obviously, the hash value, if the hash value that is received and the hash value that is calculated on the receiving end are not the same, then the digital signature is invalid. So we do not trust that message. Now, coming back to why encryption using private key was necessary as opposed to public key, which we studied a little while ago. Interesting thing here is that if, for example, as a user A used user A's private key for encrypting data. Now let's just say a user XYZ pretends to be user A and sends you some data as user A. Now, the thing is, it's encrypted and it's encrypted using a private key. Now, obviously, since encrypted using private key, user A's private key is only with user A, and this other unauthorized user, this fake user, user XYZ, will not be able to replicate that key. So the user XYZ will use their own private key and encrypt the data. Now they are pretending to be user A. Now when I receive data from user A, this so-called user, this fake user A, I will be prompted to use user A's public key to decrypt the data. Now what will happen? That key will not work because again, private public key pairs. So in which case, the user A's public key, which I'm using to decrypt, will not work with this fake user A's private key because it's not actually user A. And therefore, this authentication is perfectly, applicable here. I should not trust the message because it's not really who they claim to be. So what we can do here is that if it was really user A, then user A must have used their own private key. And when I receive a message from this real user A, I will proceed in using user A's public key, in which case that private public key pairs will match and the data will be decrypted. Now, when the data is decrypted, what will I get? I will get the hash value and the hashing algorithm. I already have. I have the plain text message. I have that plain text message plus hashing value. I will get a hash value on my side, and I just decrypted the hash value sent from the user. I will compare these both values, and if they're the same, then the message can also be trusted. So this is how digital signature is created. Now, if you can see this diagram over here, this actually summarizes what we just said. So this is my plain text. I apply a hashing algorithm and get a one-way hash value. This hash value from the sender side is encrypted using the private key, and a digital signature is created. This digital signature is then sent along with the original data, is sent over the network. Now, on the receiving end, I will take this digital signature, decrypt it using the public key. And if it works, then it means it really was who sender was claiming to be. So I will get this one-way hash value. And then I also have the original data and also have the hashing algorithm. I'll apply the hashing algorithm to the original data and get a one-way hash value. Now, if this hash value is equal to this hash value, which I just encrypted, that means data can be trusted. So this is how a digital signature is maintained. Another method is known as digital certificates. Now, this is something different. A digital certificate is issued by a trusted third party. Usually this is the certification authority or the CA, which proves the identities among users, both senders and the receivers. Digital signature is used to attach public key with a particular individual or entity. A digital certificate contains the following information. It could be the name of the certificate holder. It could be a serial number which is used to uniquely identify certificate. It can be the expiration dates. It could be a copy of certificate holder's public key. So whenever I want to communicate with that server, and I will be requesting their digital certificates, they will provide me with the public key so that I can assist in further communication. Digital signature of the certification issue authority. So this certification authority, I should be able to trust that it's not a fake certificate, it's a real certificate. And how do I know that? Is basically the certification authorities digital signature is also attached. So I can verify that it really is certification authorities using this method right over here, and it's not any other fake. So basically what it is that it's encrypted using digital certification authorities private key, and if I try to decrypt it using certification authorities public key, it should work. If it doesn't work, I should not trust it because it's not the real certification authority, it's someone else. Digital signature is used to verify the messages is sent by a known user and not modified, while digital certificate is used to verify the identity of the user, maybe the sender or the receiver. Both are used for security. Most websites use digital certificates to enhance the trust of the user. So basically your browser also requests for this whenever you're communicating with a server. Okay, let's further continue on digital certificates. The authenticity only confirms to the user that the message was sent from a person who had sent them the public. So basically, it could be anyone could have a public key. So I need to be sure that it's not someone who's pretending to be someone else. It does not consider the fact that someone might create a public key and pretend to be someone else. A more strict way of ensuring authentication is needed, and this strict way is with the help of digital certificates. The certificates are issued by the trusted third party, the certification authority, which proves the identities among both senders and receivers. Digital signatures are used to attach public key to particular individual and entity, and these are the contents of the digital certificates. Now, what happens when a digital certificate is needed? So, how a digital certificate is issued. So, step number one, the person A who requires a digital certificate contacts the certification authority. An individual person A who would be the receiver has a public private key pair contacts with the local CA. So obviously they can communicate with them. So they get in touch with them and they use the CA's public key to send them requests. So anyway, the CA confirms the identity of person A if person A's public key, if person A's public key is given to the certification authority. Okay, by the way, this method is needed for whenever we want to create a digital certificate. Okay, so as seen in this diagram, this person A, who has a public private key pair, sends his public key to the certification authority. The certification authority will use the person's A public key and their own private key and to create a digital certificate right here. Now, why are they using they will encrypt their own information, their own digital signature using their own private key, because as mentioned before, we need to be able to trust the whether the certificate is authentic. So obviously the certification authority will use their own private key to encrypt their digital signature. And once that is done, if I am verifying this a person's digital certificate, person A's digital certificate, I should be able to access the certification authorities information using their public key. And if it doesn't work, that means it really isn't the certification authority, it's someone else. So basically, the individual A who will be receiving the certificate has a public private key pair and they contact the local certification authority. The certification authority, after confirming the identity A, takes the person's A's public key and creates a public key certificate. This is known as the digital certificate, and writes the person's A public key into this document. So that's basically that digital certificate. Among other things, as we mentioned, discussed before, this digital certificate contains the person A's public key. And the CA certification authority uses encryption with their own private key to add a digital signature to this document. So if we look at the certificate, we see the person's A public key and also certificate A's digital signature. So we can verify whether the certificate is true or not. This digital certificate, after being created by the certification authority, is given to person A, and this person A will then post it on their website. So among other things, such as the date, the person, there's unique serial number, for example, the person A's identity. Apart from that, we have person A's public key, this digital signature for certification authority, and these are the contents of the digital certificate that our browsers use commonly to enhance their trust on a particular when communicating with a particular server. And if a certificate is not available or it's not trusted, your browser warns you. It creates a, it crosses out the HTTPS portion and it tries to warn you that this SSL is expired, this website cannot be trusted, whatever it tries to warn you. But if it can trust the website, if the SSL certificate is valid, then your browser doesn't bother. It gives you a green a padlock icon showing you that yes, this is trustworthy website, and your communication is handled in a secure manner. Okay, now let's talk about the secure socket layer and the transport layer security. Secure socket layer SSL is primarily applied using a client server infrastructure. So basically, client server architecture governs our majority of internet traffic. So we are clients and we seek services from different servers. As discussed before, the TCP services the application layer through various ports. The combination of, this is discussed in Unit 17 before, the combination of an IP address and a port, this makes up the socket, and secure socket layer is basically related to this term. The SSL serves as an additional layer between the transportation control protocol, between the TCP in the transport layer and the application layer. When SSL layer is active, the protocol goes from HTTP to HTTPS, and this is visible on your address bar in your browser. Apart from which, the following steps also take place. When following the SSL protocol, the following steps take place. The handshake protocol creates a session that allows the client and server to communicate. So this is the initial step that creates the communication duration, the session. Both parties agree on encryption algorithms and session keys that are going to be used in transmission. There will also be a verification of digital certificates. Once the above has been established, SSL will allow for encrypted transmission between the client and the server. So basically, if there is any third party eavesdropping on transmission, they will not be able to understand what you are saying because the data of transmission will be encrypted. The data will also be compressed and checked for integrity during the exchange. So it's quite possible that during data transmission, there could have been some data corruption or data modification, in which case we have hashing, as we studied a little while ago. The hashing is a method that is used to make sure the data has not been changed in any way during transmission. All data related to encryption is reset once the session has been completed. So once the transmission is finished, and if a session is finished, so basically if session is finished, that means the transmission is also finished. If you want to restart data transmission, you will have to create a reset, a new session, and the handshake protocol will also have to take place again. With HTTPS information such as credit cards, sensitive information such as credit cards, banking details can be shared without it being falling in the wrong hands. So usually usually websites are all HTTPS. So basically it allows for a more trust in the data transmission. And that means that when data is being transmitted, you can trust that no third party unauthorized user is listening in on the transmission. Some interesting details of SSL include, although SSL secure socket layer is referred to as a protocol set of steps, it is in fact actually a protocol suite, which we actually studied before is actually a group of protocols and sub-protocols. There is a record protocol that deals with the format of data transmission, and there is a handshake protocol responsible for security. So basically these two protocols combined are part of the SSL protocol. The operation of SSL happens without any action from the user. So basically, you as the user, you're not in control of this. It's going to happen regardless of whatever you do. However, the only action that you possibly may have performed is that you wanted to get in touch with that server. So after that, once you wrote that URL or you clicked on a link, after that, this step is automatically taking place and you are not in control of it. The starting point for SSL implementation is a connection between the client and server being established by the transmission control protocol. The client browser then invokes the handshake protocol from the SSP suite. The handshake protocol requests from the server its SSL certificate, which is a digital certificate confirming its identity. The server sends its SSL certificate plus its public key. The browser uses this public key to encrypt a key which is used as a one-off session key for symmetric key encryption to be used for data transfer during transmission. So this is the method that we discussed before. This is how key distribution problem and transmission of symmetric key is handled through using asymmetric encryption. So basically, instead of sending any data, my browser first just sends the symmetric key using asymmetric encryption. There may also be a need at this time to agree which encryption algorithm is used. So that afterwards, data transmission are encrypted, that all data transmission is encrypted using these encryption algorithms, which are agreed upon both the client and server. Okay. Okay, we're gonna stop this lecture now. In the next part of the lecture, we'll be discussing quantum cryptography, and then we will look at different techniques in separate videos, of course, regarding asymmetric and symmetric encryption techniques. So take care and thank you.